Okay, let's take a look now at the Identity API, which actually bridged the PKI to CK. So what is the problem? Government signs passport data with P256, which is a NIST standard. Verifying P256 inside a CK circuit is impractical. Wrong curve, too many constraints, you need a bridge. So the solution is resigning with the JubJub elliptic curve. So the Identity API is basically a credential issuer IDP that does the following. Receives government signed passport data. It verifies the P256 signature of chain normal cryptography. Then resigns the credentials with the JubJub ZK-friendly curve, and finally returns a signed credential of type passport data the contract can verify. So how this is implemented within TypeScript? We see here that we have a file called credential service.ts. Something nice in here is that we are calling some of the pure circuits of our contract. So these circuits, we can use it within Compact, but then we can export that into TypeScript so we can have the same logic. So we can see here that this function called sign, we are declaring a credential of type T that extends the passport data, and then we are doing some calculations. The important ones here is that we are calculating K, which is the deterministic nonce from pure circuits. So we are calling our contract pure circuits, D generate deterministic K, and we are passing the values. Then we are calculating the EC mule generator from module K, and also calling these pure circuits compute challenge for credential. So these properties are really nice because in that way, for example, here is this key inside. The Identity API uses the contract's own pure circuits, generate deterministic, which is this one here, and the compute challenge for credential, which is this one here, coming from the pure circuits, to compute the signature. These guarantees the signing follows the exact same math the contracts verify circuits expect. No mismatches, no incompatible encodings. So this same circuit, it's being used within Compact. Okay, so let's see the trust chain. The passport holder has the physical document. The government does the P256 signature. The government signed credential. The Identity API verifies the P256, resigns with JubJub. So at the end, we have this signed credential of type passport data. Then we have that within the Vestor wallet, which holds the credential locally, and with that, it can submit a circuit input. So we have the real-world asset contract, which verifies that JubJub signature in CK, and if the proof is valid, then it can happen the Merkle tree insertion. If the user it's within the Merkle tree, then in the blockchain sees it's authorized and it can interact with other circuits. Okay, let's talk now about the real-world asset API, which is the SDK layer. This SDK wraps all contract interaction behind a clean TypeScript API. There's two entry points. One, it's the real-world asset API that deploy. This is a one-time, creates quiz commitment, sets IDP key, deploys contract. And then it's the real-world asset API subscribe. This is ongoing, connects to deploy contracts, loads, creates private state. So how do we handle the state management within the UI? For that, we're using this structure under index.ts. We have the combined latest. All these are functions from the RxJS library that allow us to interact with WebSockets and real-time data coming from the indexer in this case. So the state, we're using combined latest, and we're grabbing information coming from the public data provider and the private state provider. So these are two streams of data that we are interacting in real time. Whenever each one of those states changes, we want our state to change as well. So we're using this format, grabbing this stream of the public data provider, and at the end we want the contract state, specifically the contract state data, and from the private state as well. Whenever each of those states changes, we're going to update this structure of information that we want, which is our secret key, our public key, THF balance, and TBTC balance. And then we have this auto retry on WebSockets disconnect. So the pattern combined latest merges two streams, public ledger state from the indexer and private state from local storage. Every time either changes, the UI gets a new derived state object. The retry handles transient WebSocket disconnections. And within this SDK, once we have subscribed to the contract, we have different methods. For example, we can call API mint, passing the amount. We can call the API the method provide TBTC, passing the coin. Then we have buy THF, and we pass the amount. And we have sell THF, the amount. And we have the onboard, where we pass the quiz, the amount, and the credentials. So we have the different methods, different ways to interact with the contract. We don't need to worry about how this was integrated within Compact or the different TypeScript methods. We just need to grab the SDK, the API, and call the different methods available. Okay, let's see the full stack integration. Let's go part by part. First, the wallet connection. We have things to worry about. Check the Lace extension install. So how do we check that? By using this window that midnight.mn_lace exists. If that happens, means we have our extension installed in our browser and we have this information available within the window object. Then how do we know if it's already connected? We call connector is enabled. How do we prompt user approval? We have this method connector.enable. How do we get addresses and balances? We get the state of the wallet. And how do we get persistence? We have to do auto reconnect from local storage or reload. Nice things, you can implement those methods and methodology by your own, but there is different architectures and examples like this repo, and we have also the Edda Labs starter template where we offer these wallet widgets where you have everything integrated, the wallet UI with all these different best practices. Okay, what else they have implemented in this repo? The integration with different providers. We have already been talking a lot about providers, which is the way how Midnight.js interacts with the different instances. In this case, we have the public data provider, which is indexer connection. We have the private state provider, in this case implemented by using the level DB. Then we have ZK-config provider. This is cached, fetched, one of the outputs after compiling our contract. Then we have the proof provider connected through HTTP. Then we have the wallet provider, in this case using Lace, and the Midnight provider, again using Lace. Then we have a transaction lifecycle. Let's take a look at this lifecycle. We have downloading prover key, proving transaction, signing with Lace wallet, submitting transaction, and waiting for finalization. So this pattern you're gonna see a lot happening when we see how the information is sent to the blockchain. You need first to create a transaction, you need to sign the transaction, you need to append the proof, and then you have to submit that to the node. And then it gets uploaded into the indexer, and the UI receives the updated information from the indexer. So why this matters for UX? ZK proof generation takes time, 30 seconds or more. Without feedback, users think the app is broken. This callback system keeps them informed at every time. So all this information is being tracked in real time. So whenever, this is something nice to have within UX. Whenever the user interacts with something, they need to be informed what's going on. Otherwise, they think the application has stalled. Okay, the onboarding flow. how it works. The user answers 6 questions, accreditation quiz, multiple choices. This is going to be the UI. He's going to submit, he's going to call the identity API post sign, and it's going to get the signed credential. Then calls API onboard with passing the quiz results and the signed credential, and this is going to trigger the onboard circuit. It's going to attach the ZK proof generated, which was generated, and the transaction submission, and then Merkle tree updated. And finally, the user redirected to main page can now trade THFF. Okay, the trading flow subscribes to a real world asset API state, leave THF, TBTC pool balances, and then buy the token by using this function is authorized, send, check, swap TBTC for THF. Then it sells THF and it's authorized. And then the state observable updates and the UI renders. So all this communication we've been talking on the last slides, but this is how in the UI it gets connected all together, and then finally it renders in the UI so the user can see what's going on. Wow, this was a big chapter. We have learned a lot during these episodes. So let's grab all the things that we learned and let's create a summary together. So what the chain sees versus what stays private. On chain, we have the investor authorized. It's a Merkle tree entry. We have nationality code. We have coin value for wealth check, quiz commitment hash, trade amounts, identity provider public key, what's off-chain, private, who the investor is, name, passport number, sex, exact total wealth, quiz answers, investor identity behind each trade, credential contents. So 3 things to remember. ZK identity verification equal compliance without surveillance. The contracts proves nationality, accreditation, and wealth, without ever seeing a name, passport number, or date of birth. This is the pattern that makes institutional DeFi possible. Second, JubJub signatures are the bridge from traditional PKI to ZK. Government-issued credentials can't be verified in ZK circuits directly. The identity API resigns with a ZK-friendly curve, and the contract verifies inside the proof. 2 signature schemes, 1 trust chain. And lastly, we have the Merkle tree authorization is scalable permissioning. Once onboarded, every trade is gated by a Merkle membership proof that the tree grows with each new investor. No gas heavy mapping lookups, no public permission list. So the onboarding is just one time. And then once you are in the Merkle tree, then you can keep operating on the different circuits that you are allowed. So what's next? The repo, it's open source. You can find it under this link on the Brick Towers organization. You can fork it, read the contracts, trace the onboarding flow end to end. You can watch the explainer where we did a quick version of why ZK identity changes everything for real world assets. And then we did as well a deep dive for a detailed breakdown of JubJub signature cryptography inside compact circuits. So you can watch the explainer and the deep dive regarding this contract as well. And if you're building tokenized assets, compliance infrastructure, or AI agents that need to prove credentials without exposing data, we help teams exactly for this. So links in the description. See you in the next episode. Bye bye.